Welcome back. So hopefully you had a good time about the last lecture talking about the um, physical meaning of the determinant. Well, for some students, they have learned the determinant in our classes before. However, they have trouble understanding the meaning of that. So that's why we chose the geometry definition to show you um, how the definition of determinant formed and how we're going to use it. And that's the core content of today. All right. Welcome back. Well, hopefully you have enjoyed the courses talking about the linear algebra. Okay, so in the last lecture, we talked about the definitions and also the linear dependent and independent theorems about the linear algebra. So in today's lecture, I think you probably have got the idea. Yes, after you know the definitions, which is about the concept, we have to get into the properties discussion. You know, that is mathematics flow path. So in the section of determinants, we have 7 major properties. So let's talk about one by one. Remember, in the class, talking about the geometry definition of determinant, we have a very simple example here. So we have 1AA, 1A2, 1, 2, 2, 1, A, 2, 2. Okay. Okay. So here we said that this is corresponding to, two vectors. If we take each row as a vector. So these two vectors, as long as they are not linear dependent, they will form an angle. And then we can further form a parallelogram and calculate the area, which is corresponding to the determinant value. Okay, so that's the geometry definition of determinant. So we understand that we used a row vector in our definition. However, if you look at some textbooks, you will see that most vectors in the linear algebra are the column vectors. So no matter if it is for matrix or further for determinant. So usually we take this one as a vector. So we call it a column vector. Okay, so you can have a wonder. So if we transpose, for example, we will say for the determinant A, we do the transpose, which means you just rotated, this determinant by 90 degrees, right? So for example, we have this example here. You have a determinant 217, 0, 9. I would say this one is 5. Just arbitrary generated numbers for you guys. Okay, so if we do the transpose, now we can have, the column will become row. So we have 2, 0, 4, 1, 9, 11, 7, 5, 3, right? So are they equal? Yes, they are equal. So in the linear algebra class, we will now talk about the proof of this theorem. However, please just remember it. And that's the fundament for us to write the vectors more conveniently. Well, if we have to write column vector, for example, which is 217, which is this one, right? So it kind of takes more space. And also, even if you write it on your notebook, test paper, or blackboard, it's gonna be a little, time consuming compared to the row vector 2, 1, 7. Yeah. So, that's why we have this first theorem talked about. So no matter if your determinant or matrix is column vector or row vector, their determinants will always be the same. Okay, so this one is like identical to this one for the determinant. All right, so in the future, so in this class or in your linear algebra class or the textbooks you're referring to, you will see that your level will use the column vector. So for example, so for this determinant, of course, it is composed with different vectors. For example, we will say alpha 1, alpha 2, and alpha 3. And for each alpha, it is not only a single number, but a column vector. So for this one, for alpha 1, we can change it to maybe, I would say, A11, A12, A13, blah, 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 A1n, for example. Yeah, similarly, we can do the transformation for other column vectors. All right, are ready for the next property of the determinant? Here we go. So if I write a determinant like this, alpha 1 to alpha I minus 1, so there are a lot of columns vectors between them. I just ignore them. And suddenly after alpha I minus 1 vector, we have a 0 vector. And then we have, the other common vectors like, alpha I plus 1 and all the way to the last one, alpha n. Okay. So basically, the 0 vector here is the ith vector for this determinant. And here, please pay attention to the 0. It's not the regular 0 we have been learning for so many years, which means it is not only a single number, but a vector. So this one equals to a column vector 0, 0, 0, 0, 0, right? Okay. So some students may propose a question like, so why don't we write 0 like this to indicate it is a vector? Because that's what we have learned in the calculus. Yeah, we don't have to, because calculus is calculus, and this is algebra. Yeah, this is algebra. Linear algebra is part of the advanced algebra, and we're just talking about the vectors and matrix. So we don't have to use the notation arrow to differentiate between the regular number 0 and vector 0, like what we have done in the calculus class. This is the professional algebra class. So we can just use 0 to stand for this whole bunch of zeros. All right. Okay, so if I ask you, can you tell me the value of this determinant containing this 0 vector right away? I think you have to think about it. Okay, you got it? So I would say this one equals to 0. Surprised? Why? Well, in a lot of textbooks and also in a lot of mathematics classes in colleges, the teachers will ask you to remember, the theorems, or just tell you to, maybe find out some small examples. For example, we have, this 1, 2, 3, 0, 0, 4, 5, and ask you to try it. Yeah, I will not say this is not a good idea. Yeah, I will use the same trick sometimes. However, in my class, like what I told you in the first session, I want you to establish the mathematics philosophy, which is not only useful for the math class but also useful for your whole life and your whole career, to lift up your mind to a whole new level about how to think. So, like what we talked about the definition of determinant from the point of view of geometry. So this one, we're going to continue to think in that high advanced level, to use some abstract, thinking pattern to resolve such a problem. So from the definition of determinant from the perspective of geometry, we understand that, for this determinant, which is composed by these vectors, which is corresponding to the vector in the nth dimension space. Okay. Yeah, I know. Yeah, we understand that it sounds very abstract. However, please try, and then you'll find out that, wow, those high-level thinking is fast and also cool. Okay, so for example, if we define n equals to 2, so we have a two-dimensional space. So this time, naturally, we're going to have form a parallelogram here. So you can see that usually we can form such one and calculate the area because there is the area. However, if one vector here equals to the 0 vector, which means this one become a point. So this one becomes something like a point. Okay, so we cannot form a parallelogram anymore. So that's why we will have the area as 0, and the area corresponds to the determinant value. So that's why the determinant here equals to 0. You would say, that sounds very cool, but I'm still kind of confused. How about we try some hard space like the n equals to 3? Yes, we can try it too. Okay, so if try this. Okay, so we have 3 vectors to form such volume for us. Okay, this one I would say like this. Okay, so for this one we can see that we have a volume here. Okay, but if we shrink this one, for example, to 0, because we have a 0 vector here, so we're going to have this. Okay, it seems like the volume will become 0, and the volume here corresponding to the determinant, which has 3 dimensions. All right, so we understand that. For example, like this one, right? So if we are in the single dimension, we have this as length. Of course, this is now 0. However, in the two-dimensional concept, we're talking about the area. So the one line cannot have any area. So that's why the area equals to 0. So similarly, so in the three-dimensional space, although the two vectors can form such area, however, the third vector becomes a point. So that's why we cannot make a volume. So even though we have an area, we don't have a volume. So similar, we can imagine to higher conditions. So in such condition, so when one vector, at least one vector becomes 0, it means the volume in that nth dimension n dimension will become 0. Although, you know, the n-1 dimension still have a value, but the volume for the n dimension will not exist, or to say that it will becomes 0. All right, so see, we don't have to, you know, try many small examples or just remember such property, um, you know, by heart. You know, we can just draw and think in our mind. And when you practice a lot, you don't even have to draw it. You can just form such a picture in your mind. So you will naturally find out the solution by yourself within 1 second. Yeah, it must equals to 0. Alrighty here. So we're going to talk about third property of the linear algebra's determinant. So I just change one thing here, a change in the coefficient for this vector. So last time we just put a 0 here, right? So to make this whole column to be 0 column vector. Okay, so I just changed, you know, to k for the coefficient to make it look like k times of vector alpha I. So here we have, you know, the regular column vector alpha I, and here we have, you know, k times of it. So what will the determinant become? Well, last time we used a very abstract thinking, which seems to be difficult at the very beginning, but turned out to be cool and very useful and fast later if you stop to be scared about it and practice. You will find it to be in that direction. So this time, can we do it again? Yes, we can. So last time we said that if we are in a two-dimension condition, right? So if this vector becomes 0, you know, shrinks to be 0, so of course we cannot form the parallelogram and the arrow will become 0. So this time, if we have a vector, yes, which is, you know, k times of another vector, this one. So it seems like, for example, we have a ki, you know, the alpha I here, right? And k times alpha I just means we just extended this vector to k times. For example, the k equals to 3. Okay, so we will have the length of this one, you know, to be, okay, you know, the whole length of this vector to be 3 times of this vector. All right, but anyway, they are, aligned, in the same direction. So in the last lecture, we defined such condition as linear dependent. And we say that determinant of this, of course, is 0, just because they are in the same direction, within the same line. So there's no parallelogram for them to form. Yeah, so that's why the area still equals to 0. Yeah, this one equals to 0. And, you know, this is more like a general condition of the property number 2, because last time we said if k equals to 0, we say the determinant will become 0. And this one is like when k is now 0, it is more like a 1, 2, 3, blah, 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 blah. But we say that the determinant is still equals to 0. And the reason has been explained here too. Well, that's all for today's class. We're talking about 3 very important properties of the determinant. So hopefully you can review today's lecture and also the definitions of the determinant too. And in the next lecture, we're going to continue this very exciting topic, the properties of determinant. See you next time.